So all right. Thank you for the introduction. It's a nice idea to have such virtual reading seminars, and it's my pleasure to tell you what we learned about how neural networks learn using methods from statistical physics and dynamical systems. I'm a physicist, and my main research interest is in fluid mechanics, turbulence. And these are very high, turbulence is a very high dimensional system, and you have to think of ways of deciphering, structuring, understanding the structures of the high dimensional phase space of this nonlinear dynamic system. And people developed a method that's called Lagrangian coherent structures. And we realized that those could be used to analyze how a neural network learns. And these Lagrangian coherent structures, certain types of them, are ridges of Lyapunov exponents. So I wanted to explain to you what the Lyapunov exponents are and how we use them to understand how neural networks, how a fully connected neural network learns in very simple examples. And then I try to make some general conclusions from this. That's the goal. Now, I'm not quite sure how much time that's going to take. So if there's some time over, I will briefly comment on how you use also these Lyapunov exponents to understand how to choose parameters for reservoir computers. You know, they have been used with great success to predict time series of nonlinear origin. But the question has always been how to choose all the parameters. And there are some household recipes, but not really a thorough understanding of what's the physics or what are the parts that determine the parameters. So if there's time, I will talk about that. And so that's the second paper here. And the first one is what I just first described. And they were done by my student Ludwig Storm and together with some colleagues in Gothenburg, campus, Christian, and a fluid dynamicist in Nice in France. Um, okay, and so you all know the XKCD cartoon about what machine learning is. So the question is it really just linear algebra? Or can we understand the mechanisms that allow the networks to learn in more detail and understand something important about it? And of course, my answer is no. It's not just linear algebra. And so the general context is a very simple layout, a feed-forward layout with capital N neurons per layer, and here capital L is the number of hidden layers, and then I have usually really simple classification problems, patterns black or white, so a single output suffices to do that. And that's very crucial for some part of the talk, only two inputs. And the reason is I want to look at the input space. I want to see how patterns from different regions in the input space, how they are mapped. Okay, and so the very general question is of course, these algorithms, they've been around for a very long time, and then suddenly people realized now the algorithms work really well, and so the question is, what is it that makes them work well? Because the algorithms essentially are the same as those from the 80s or even the 60s. And another general question is, and that connects to what people call exponential expressivity. How does the network represent the things it learns about the data set? And then we had a more practical question, and that was a colleague of mine who looked at different networks. They had a physical realization of a network, and so they asked if I distribute my neurons in different ways. For example, I make many layers with only few neurons, or two layers with many neurons. Um, how does that network layout affect the performance? does the performance depend only on the total number of neurons? No, it doesn't. Right. And then there's a connection of what I will tell you about to the neural tangent kernel. So ideas of describing how neural networks learn in the limit when the number of neurons per layer becomes very large. Well, in fact, the neural tangent kernel means infinite. And so then there were some recent, now perhaps not so recent papers anymore, that showed that, yeah, if you don't look at infinite width, but very large only, though finite, then the networks, in some cases, learn quite differently. And so we wanted to understand how that transition comes about. And a bracket question for all of these questions is, the last question that I have here, how sensitive is the network output to small input changes? That is relevant for all of these questions that I've described above. So I want to start with this. And of course, this is something the practitioner needs to control very well. You modify your input a little bit in a classification problem by how much does the output change. And so we will try to understand this. So by the way, perhaps if people want to ask questions, because I'm afraid that I will maybe waste your time telling you things you know, or that I go too quickly over things that you don't know, and then it's a waste of time for you. So maybe it's better if people can ask questions, but that's not what you do normally, is it?
We usually postpone the questions until the end, but if
Okay.
people have questions, maybe they can put these questions on the chat and
Yeah.
you can see
I would be
them.
really grateful if you could. Uh, uh, and it's a little bit tough for me to monitor the chat, but if you could shout out if there's a question on the chat, then I will answer it.
Yes, we will monitor the chat. Yeah.
Okay, great. Okay, so the framework we use to try to understand the sensitivity of the output to the inputs, it's based just on the notion that this recursive mapping that tells us how the signals are mapped from layer to layer until they reach the output. Here's the nonlinear activation function. Here are the inputs in the layer before. These are the weights, and I call these thresholds. That looks like a discrete dynamical system. A nonlinear system, an iterated system that can show exponential sensitivity to small changes in the input. In fact, that can show chaos. And so the question is, if you iterate this, do you get chaotic motion or not? Should you strive for chaotic motion or not? At first, it seems, how can the network produce anything meaningful if the mapping produces chaos? Now, chaos is, of course, something that's defined in a dynamical system where what you change is time. The question is, how do variables change as a function of time? Either continuous if you have a differential equation, or discretely if your system evolves in discrete time steps, like a population, for example, from generation to generation. And here, this is a discrete dynamical system, and you see that's the state in layer L minus 1, that's the state in layer L, and we just interpret the layer index as time. That's it. And I wanted to say that it's really important. There are other notions of time, of course, regarding this neural network. For example, training time, how many epochs you need to train. That's not what I'm referring to. So the time steps, when I say time steps, because my language is dynamical systems theory, it means layer index. Okay, so I think I will skip over the rest. The rest is just an explanation that these neural networks can be a little bit more general than the standard dynamical system. I don't think it really matters for this brief summary. So the crucial point from this slide is that a neural network, the forward mapping, is a dynamical system. All right. Let's see now. That's it. Okay, so now this slide contains some equations, but it's really rather straightforward. And what I'm summarizing here is equivalent to the work of Poole and Pennington from about 10 years ago. However, I wanted to say that this stuff, it was known in dynamical systems theory a very, very long time ago, because the question that Poole and Pennington asked about the neural network is the standard question in dynamical systems theory. And the question is the sensitivity question. If you change the inputs a little bit, by how much do the states in the last hidden layer change, for example? And so I called these states x0. And so a small change is a delta x0. And how will it be mapped to the changes, in layer L, for example, this one? And so all you have to do is differentiate this. And because, of course, as you know, you have the nested structure, X is G of G of G of G, the result is a product. You get a product of matrices. So these are the different weight matrices in the neural in the different layers, and these here are diagonal matrices that have elements, the derivatives of the G prime. And of course, that's the structure you analyze when you do the backpropagation, because there you compute the gradient. The gradient takes the derivative with respect to the weights, but here you take the derivative with respect to the inputs, but it gives a similar structure. So, if I change this a little bit, by how much does that change? Now, that question is easily answered if you are at the early stage of the learning process where you initialize the weights randomly, because then these W's are just random matrices. And okay, so you've got the diagonal matrices in between. And so in that case, you see that the sensitivity is determined by a product of independent random matrices. And there is a mathematical theorem, the Oseltic theorem, that says in this case, one can prove that the perturbation, it grows or shrinks depending on the the properties of these matrices exponentially. And that's shown here. So you see, delta x0 is the initial change to the input. Delta xa is the change to the neuron in layer L. The logarithm is applied to this ratio. I should have perhaps put parentheses around it. And if you have consider very many layers corresponding to the long-term dynamics of a dynamical system, you get a definite number, and this number is the number that Poole and Pennington calculated, and it expresses, it determines the exponential expressivity of the system. It tells you by how much a small change in the input grows, and it grows, because this becomes a constant, exponentially. And that's valid when the initial changes are small, just a small perturbation of the input, and you take the limit of infinitely many layers. Now, these people knew that if at the same time you not only take the limit of infinitely many layers, but also infinite width, then everything becomes very simple, and you get that this exponent is just the log of essentially some number of order unity times n times sigma squared. This is the variance of the randomly chosen initial weights, and their mean value is 0. So that and that immediately tells you what is a, so this is what Poole et al. In part observed. It immediately tells you what's a good choice of your variance of the initial weights. Well, maybe you don't want an exponential instability, that the tiny differences grow exponentially. Maybe that causes problems. You certainly don't want that that lambda is negative, that all differences between the inputs exponentially go to 0, because then you can't classify anything. So perhaps a good choice is that lambda is 0, which means the input changes neither grow nor shrink exponentially. How do you get that? Well, you get that if the argument of the logarithm is 1. So what you should choose is sigma squared proportional to 1 over n. This is the famous rule of how you should choose the initial weights in a network of width n, and it follows immediately from this. Well, I say here random matrix theory because this was derived as a part of random matrix theory. People trying to analyze the dynamics of chaotic systems where correlations decay rapidly, so that this and this and this are uncorrelated from each other. And since it's a chaotic system, they look essentially random. Yeah, and I wanted to show you the book. I think it's a fantastic book about exactly what we need to understand regarding how signals are mapped backwards and forwards in a neural network. And it contains an enormous amount of mathematical results and insight. And so, this guy, he got a Nobel Prize some years ago and wrote the preface and lauds the book highly. And I think it's a fantastic book. So I wanted to recommend it to you. All right, all of this very well known. So now the only thing we did, and I think it's sufficient just to look at this picture, or maybe this equation. The only thing we did is we said, well, a neural network, it doesn't have infinitely many layers. It only has a finite number of layers. And what changes if you don't take the limit number of layers goes to infinity? What changes? And first, what does not change? If in input space you have your input pattern and you make some perturbations in a little circle around it, it is still so that after 4 layers here, that the circle grows to an ellipse, and that this length of the ellipse here, it grows exponentially with a maximal exponent. But now I've got lots of little L's here. This, how much it grows, you can see it. It depends on how many layers you have. But it still grows exponentially. And so what people do is they define the maximal finite-time Lyapunov exponents. That's FTLE. That tells us if I have a finite number of layers, by how much do the signals grow exponentially. And that's exactly the same expression as before, exactly the same as before here, but without the limit. So the only thing we've done is we've crossed out the limit. All right? Now, what's the great point about crossing out the limit? If you have the limit, you get a definite value of lambda 1 regardless of where you start in input space. But when you don't have the limit, number of layers goes to infinity, then your exponent depends on where you start. So now you have suddenly, and this is a big difference, suddenly you have a local sensitivity. You have some regions in phase space where the exponential growth is larger than in other regions. And so we wanted to look, if we make a map of what this exponent looks like, this sensitivity exponent, over input space, what does it look like? And that was motivated by the Lagrangian coherent structures. They are okay. No, I will show you the example first. Sorry. So here, okay. So question is, in a very simple example, how does it look like? And so to plot the lambda one, how it depends on inputs, I show a very simple classification problem. So just a target that can be plus or minus one. It's corresponds to the single output here, and you have two types of patterns with plus one or minus one, and the minus ones are inside the unit circle. And so now Ludwig trained the network so that it has a very good classification accuracy. Here it's stated 98%. And then he plotted the sensitivity exponent. And the result is shown here. And so this is, please forget about these lines. They are not important for our present purpose. The only thing that matters is the color. And so what you can see, the network, it finds the decision boundary. And it has a high sensitivity, a positive exponent equal to something like 4, near the decision boundary. But inside the decision boundary and outside, it's mostly blue, so the exponent is much smaller or even negative. So the question is, okay, so and this here, a ridge of large Lyapunov exponent, is called in fluid mechanics a Lagrangian coherent structure, and these are just two examples. You have my slides, so you can look at these references. There is too much background to explain precisely what they tell us about these fluid dynamics problems, but they are these ridges of large Lyapunov exponents are used to understand how phase space is organized in dynamical systems. And so here, these ridges tell us how phase space is organized in the input space, how the input space of a neural network is organized. So, question. Does this tell us anything useful? Or is it obvious? You could say it's pretty obvious. It really just only tells us something that we should have immediately guessed in a very complicated language. And so let me just be the advocatus diaboli. So I would say, look, this is obvious. If you have an input pattern very close to the decision boundary, extremely close, if you push it over the decision boundary, the target should change. So you need a change here of order unity. But if you push it only exponentially, 10 to the minus 6 or so over the decision boundary, then this little change needs to grow by a factor of 10 to the 6. And so that requires exponential expressivity, that requires a large exponent so that the small change is exponentially amplified. But if you start in here, these are all the same patterns. They should all get the same classification. So if you change something here, the output should not change. So the exponent should be negative. So I could say this is just a very complicated way of representing the decision boundary. And you can see that the network learns the decision boundary. So nothing particularly revealing. And so now comes, I think, the interesting part. And that is Ludwig plotted these ridges of high sensitivity in input space. Where in input space is the output sensitive to small changes of the patterns for different networks of different number of layers and different number of neurons per layer. And here you can see that the network learned the decision boundary really well, but here there's no trace of the decision boundary. This is many layers, few neurons. This is few layers, many neurons. So, here you get in the regime of the neural tangent kernel. And so I thought at first that this picture means that here the network has learned very well, so the classification accuracy should be very high. And so here probably the network hasn't learned very well, and so the accuracy isn't so great. Well, it's not like that. All of these networks of different layouts have the same very high accuracy. They all classify extremely well. But you can see that this network, it learns the decision boundary. But this network, it doesn't learn the decision boundary. It learns something else. And so you can see that there's a dichotomy. So networks learn at least in two different ways. And the question is, what does the network here learn? And so we looked at that. So the network, forget about these, they are the eigenvectors of the corresponding Lyapunov vectors, and we studied them to relate the findings even closer to the Lagrangian coherent structures, but I don't need them in this talk now. So this is the case where there's a tiny trace, but if you were to increase n even more, then it would be just uniform red, which means the network doesn't learn the decision boundary. But this is a network with few layers, but very high number of neurons. So what happens is that the network embeds the input data into a very high dimensional space, hidden space. And so then that as you increase the number of dimensions, the probability that a certain binary classification problem is linearly separable, it increases. And so the idea is that you have this embedding into very high dimensional space with random weights, and that embedding becomes linearly separable so that you can separate it with this single output neuron. So it's just that. But what it means is, if this is really true, it means that this should work for the random weights. There should be no training necessary. And so that's seen here. So Ludwig plotted the test error in a network that produced this, so large n and small number of layers, as a function of n, and this is the test error here when all weights are trained, and this is the test error when you have just random hidden weights. No hidden weights are not trained, and as n increases here to 100, you see that the two basically agree. So it's just the embedding, and of course you understand this is precisely lazy learning, so it connects to the neural tangent kernel. So if we go back, we see that this network learns the decision boundary, and this is just random embedding where the hidden weights need not be trained, and in other papers that's called lazy learning, because when you look as you train the network how the weights change, you see that the hidden weights change very little, and it's clear they do because you don't need to change them to get a good result. Only the output neuron needs to be trained. So that's the insight. So the insight is that there are two different ways in which this very simple network, fully connected, learns this very simple problem, either by finding a decision boundary or by random embedding. And these two ways of learning are completely different. And lazy learning is on one side, it's got nothing to do with the decision boundaries. And so if you understand lazy learning, it doesn't tell you anything about in the limit where n is taken to infinity, it doesn't tell you about the decision boundaries. Okay, and last thing, if you look here, you see a transition between the two. And so one can ask, where does the transition happen? And because of the exponential sensitivity, you find that the transition point where you go from one to the other, how, the number of neurons above them, you are in the random embedding regime. Below, you're in the learn the decision boundary regime. And so what's this critical, what's the value of n that determines whether you are in one or the other regime? That's this one. It depends exponentially on L. So you see, a large number of layers, you need to go to many more neurons per layer to get rid of the decision boundary. But eventually, as you increase the to many more neurons in the hidden layer, as you increase n, you will get something like this. Yeah. And so, okay, and now another test problem. How does it look like for the MNIST digits? That's harder to analyze, although it's also only a caricature problem, because the input space is very high dimensional, so you can't really plot it. And so what Ludwig did was he projected using the bottleneck states of an outer encoder, he projected the input space into 2 dimensions with a nonlinear projection. But then he computed these exponents, how they depend on the 600-dimensional input vector. He computed them for the full system. And so these red and blue values are the real proper exponents in the full dimension, and they are just plotted like this. And so what you can see here is, for example, yeah, you can see that the different digits, of course, as we understand, they are grouped into different clusters. So this is the 0 cluster here. And then you can see that inside you have a region of negative exponent, and you should, because these are all zeros. And then you have a decision boundary around it with positive, very sensitive exponents. And you can see that this is really the decision boundary if you correlate the classification error, which should grow if you're in the vicinity of the decision boundary. It correlates very clearly with the color. And so the last thing I want to say is that has an implication. This learning dichotomy has an implication for robustness. And so you can see that if you learn this system here, where I've left a large white region of uncertainty, and then the network with very many layers, it finds this decision boundary, which is overfitting. There is no feature in the data that tells us that the decision boundary should look like this, and it's extremely sharp. And so that's not good. Whereas in the other regime, if you have only 2 layers but a large number of neurons per layer, you get a very smooth. So the red line is some decision boundary that Ludwig later imposed. So what you should really look at is the light red and blue color, and you see that the network that does the random embedding, it correctly represents the lack of knowledge about this region, whereas the network that has many layers on a few neurons doesn't. So, in other words, the embedding has one advantage at least, it's more robust. So there's one last thing I will say, and then I will stop. So here you see this Hampus did this. He made an adversarial attack from the ninths to the fours, using the algorithm from this paper. And here's the path that the algorithm took, and you can see how the exponent becomes large, deep red, which shows that the adversarial attack goes over the decision boundary, over the ridge of large and positive Lyapunov exponents. And so the typical adversarial step in the MNIST space, they look like this. That's the changes that you do to the patterns to take them over the edge. And it's strongly correlated with the maximal Lyapunov vector, which is the pattern that corresponds to the maximal Lyapunov exponent. And so you see, of course, and that's something we know, so perhaps that's not so surprising, that wide networks are less sensitive to adversarial attacks. Okay, and so to conclude, the finite-time Lyapunov exponent is a good tool. It tells us local sensitivity. You look at the local sensitivity, how the sensitivity to changes in input space depends on where you look. And the ridges of the finite-time Lyapunov exponent, they organize the input space into different regions, basically the different classes. And I mentioned they are Lagrangian coherent structures. That's how we got motivated to look at them. And they are correlated with a large classification error and also a large prediction uncertainty. And I showed you that there are different learning regimes. Sometimes the network makes these ridges and you see them very clearly if you have many layers. Otherwise, it's just random embedding, and that determines the robustness and sensitivity to adversarial attacks of the network that has learned. Yeah, what we haven't done, or what it could be interesting, what I want to do in the future is there's something called large deviation theory, which should tell us how the finite-time Lyapunov exponents are distributed when n is large but not infinite and L is large but not infinite. And it's unclear to me how that looks, and to connect to the 1 over n corrections of the lazy learning or neural tangent kernel, that needs to be done. And another thing is the theory. I just showed you numerical results now, but in the paper we also have some results about how these Lyapunov exponents change as you train. And that is really hard to understand. Of course, to understand that, it would tell us how the network actually learns, not only how it represents what it has learned. And that's hard because when the network learns things, the weight matrices in the product are no longer independent and they develop correlations. And perhaps the brown book by Paladin can tell us about how to deal with that. Other architectures, effect of regularization that we've only started to look at. That's what I wanted. Those are 4 open questions, and that's what I wanted to tell you. Thank you.